Hello everyone, welcome back to my YouTube channel. I am Meghana Vaijay from Sri Venkateshwara College of Engineering, Bengaluru, from Department of Basic Science, CSC branch. Now I am going to discussing about the subject is Mathematics for CSC Stream 2. In this subject, the subtopic is changing the order of double integrals and definite line integral a to b f of x dx. Double integral. We integrate a function f of x comma y called integrand over a closed bounded region R in the xy plane whose boundary curve has a unique tangent at each point but may have finitely many curves. We subdivided the region R by drawing parallel to x and y axis. We number the rectangles that are within R from 1 to n, and in each such rectangle we choose a point, say xk comma yk in the kth rectangle, and then we form the sum. Jn is equals to sigma k is to 1 is to n f of xk comma yk delta ak, where delta ak is the area of the kth rectangle. This we do for larger and larger positive integers n in the completely independent manner, but so that the length of maximum diagonal of the rectangles approaches 0 as an n approaches infinity. In this fashion, we obtain a sequence of real numbers. Assuming Jn1, Jn2 continuous in R and R is bounded by finitely many smooth curves, one can show that this sequence converges and its limit is independent of the choice of subdivision and corresponding points xk, yk. This limit is called the double integral of f of x, y over the region R and is denoted by double integral R f of x, y dx dy. Change of variables in double integrals. Integral a to b f of x dx. Integral alpha to beta f of x of u dx by du into du. Here assume that x equals to x of u is continuous and has a continuous derivative in some interval, and such that x of alpha is equals to a of x of beta is equals to b, and x of u varies between a and b when u varies from alpha and beta. The formula for the change of variables in from xy to uv is double integral r f of x comma y dx dy is equals to double integral r star f of x of u comma v comma y of u comma v del of x comma y divided by del of u comma v du dv. That is the integral and is expressed in terms of u and v, and dx dy is replaced by du dv times the absolute value of the Jacobian. And here we assume the following: the functions x equals to x of u comma v, y is equals to y of u comma v. Affecting the change are continuous and have continuous partial derivatives in some region r star in the uv plane, such that the point of x comma y corresponding to any u comma v in r star lies in r, and conversely to every x comma y in r there corresponds one and only one u comma v in r star. Furthermore, the Jacobian j is either positive throughout r star or negative throughout r star. For polar coordinate r and theta, x equals to r cos theta and y equals to r sin theta. J equals to del of x comma y divided by del of r comma theta. Cos theta minus r theta sin theta r cos theta is equals to r. Double integral r f of x comma y dx dy is equals to double integral r star f of r cos theta r sin theta r dr d theta, where r star is the region in the r theta plane corresponding to r in the xy plane. Now I am giving example. Change the order of integration in the following integral. Integral 0 to 1, integral 1 to e power y f of x comma y dx dy. Since the focus of this example is the limits of integration, we won't specify the function f of x comma y. The procedure doesn't depend on the identity of f. Now I am going to give for this question solution. In the original integral, the integration order is dx dy. This integration order corresponds to integrating first with respect to x and afterwards integrate with respect to y. Our task is to change the integration to be dy dx, which means integrating first with respect to y. We begin by transforming the limits of integration into the domain D. The limits of outer dy integral mean that 0 is lesser than equal to y and y is lesser than or equal to 1. And the limits on the inner dx integral mean that of for which value of y the range of x is 1 is lesser than or equal to x and x is lesser than or equal to e power y. The region D is shown in the following figure. The maximum range of y over the region is from 0 to 1 as indicated by the gray bar to the left of the figure. The horizontal hashing within the figure indicates the range of x for each value of y, beginning at the left edge x equals to 1 and ending at the right curve edge is x equals to y is in the red curve and edge x equals to 1 is in the blue line. We have also labeled all the corners of the region, and the upper right corner is the intersection of the line y equals to 1 with the curve x equals to e power y, and they were the value of x at this corner must be equals to e power 1 equals to e, and the point is e comma 1. And to change the order of integration, we need to write an integral with order d by dx. This means that x is the variable of the outer integral. Its limits must be constant and correspond to the total range of x over the region D. The total range of x is 1 is lesser than or equal to x and x is lesser than or equal to e, and as indicated by the gray bar below the region in the following figure. Since y will be the variable for the inner integration, we need to integrate with respect to y first, and the vertical hashing indicates how for each value of x we will integrate from the lower boundary red curve to the upper boundary purple line, and these two boundaries determine the range of y. Since we can rewrite the equation x equals to e power y for the red curve has y equals to log x, the range of y is log x is lesser than or equal to y and y is lesser than or equal to 1, and the function log x indicates the natural logarithm which sometimes we write as ln x. And in summary, the region D can be described not only by 0 is lesser than or equal to y and y is lesser than or equal to 1, 1 is lesser than or equal to x and x is lesser than or equal to e power y as it was for the original dx dy integral, but also by 1 is lesser than or equal to x and x is lesser than or equal to e, log x is lesser than or equal to y and y is lesser than or equal to 1, which is the description we need for the new dy dx integration order. These latter pair of inequalities determine the bounds for integral. We conclude that the integral 0 to 1 and integral 1 to e power y f of x comma y dx dy with integration order reversed is. Thank you.